Welcome back to the AMC 8 course. Here is our first lesson on triangles. In triangle ABC, point D divides side AC so that AD to DC is 1 to 2. Let E be the midpoint of BD and let F be the point of intersection of line BC and line AE. Given that the area of triangle ABC is 360, what is the area of triangle EBF? Pause the video to try to see if you can solve this on your own. So before going to this problem, I want to go through a main concept that we're going to be looking at in this problem. We all know that the area of a triangle is determined by its base and height. Base and height are the two parameters that can be plugged into the formula, right? Which is base times height over 2 is the area of a triangle. Whenever we are comparing the areas of two triangles, we should always look at their base and height to compare them. So let's reread the problem to see what information we already know. In triangle ABC, point D divides side AC so that AD to DC is 1 to 2. So if AD was x, then DC would be 2x. Let E be the midpoint of BD, so EB and ED are the same. F is the intersection, and that the area of triangle ABC, so the whole thing, is 360. And we're trying to find EBF, which is this small section here. Well, what do we already know? We know the total, and we know a ratio, which is, we actually know two ratios, which is one is 1 to 2, the other one is 1 to 1. How can we use these ratios to our favor? Well, we know if we just looked at these two triangles over here, ABD and DBC, we see that they're basically the whole triangle ABC split up into two parts. One part is 2 times the other. Therefore, what do we know about the areas about each of these triangles? Looking at these two triangles, we know that triangle DBC is 2 times triangle ABD. How do we know that? Well, we see that they have the same height, right? Now we're comparing two triangles. We know that they have the same height, which is BD. This is the same. The only thing that is different about them is their bases. We can ignore the other side and just compare their bases. Their base, one is 2 times the other. Therefore, the total area is 2 times the other as well. So we know that triangle DBC is 2/3 of triangle ABC. So 2/3 times 360 is equal to 240. So this is the area of triangle DBC, which, to our luck, which is the larger triangle that contains triangle EBF. We also know that triangle ABD is 1/3 of 360, and this gives us 120. But we don't just stop there, because we know that this triangle, ABD, itself is 120, and it is further split into two smaller triangles, triangle ABE and ADE, and we know that they have the same area. How do we prove this? Well, because they have the same height, and because they have the same bases. So 120 divided by 2 is equal to 60. That means that each of these triangles have an area of 60. How can we continue comparing triangles to find out areas? Because as you can see, by just using the total area and two ratios, we have already found out the individual areas of multiple different regions. So how can we use the same method to find out EBF? Well, we can notice that there's lots of triangles that make up this figure, but there's also one quadrilateral EDFC. So how can we make use of this area here? Because we don't know anything about this quadrilateral. What we can do is connect EC to make it to turn it into two smaller triangles. And of course, we could also go DF, but it makes more sense to go EC so that we can take advantage of 2x, which is on the on side DC. And this is also very common in geometry problems whenever you see a larger, complicated, well, a quadrilateral isn't even that complicated, but this is not like a square or a rectangle. It is a random quadrilateral. So whenever we see situations like this, we can split it up into, say, a triangle, which we can get more information out of. And now let's see how we can continue comparing triangles to find out the area of these two portions. Well, we can find the area of EDC pretty easily. Why? Because we see that it shares the same side as ADE, right? So they have already the same side. They already have the same height. The only thing that is different about them is their bases. Triangle EDC is exactly 2 times triangle ADE. Triangle EDC is 2 times triangle ADE. Therefore, triangle EDC has an area of 2 times 60, which is 120. So we know now that the area of this triangle is 120. But after finding the area to triangle EDC, we still can't find the area of EBF. So what do we do now? Well, the only thing we know now is that since the total area of triangle DBC is 240, then the total area of triangle EBF and ECF has to be 120. That's the only thing we know, right? So we only know that this blue region here is equal to 120. But as you can see, we are getting closer and closer to finding out triangle EBF. So what is the area of triangle ECF? Well, remember, in the very beginning, we were able to find out so many areas of smaller triangles because we had 2 things. And these 2 things were the total area that they put together composed of, and we also knew a ratio, the ratio of sides. Because with the total area, and remember, they all have a shared height, and here we do have a shared height between these 2 smaller triangles, the only thing we need to know is what is the ratio between their 2 bases. In this case, we have to ask ourselves, what is the ratio between the 2 bases, which is EF and FC? What is the ratio between these 2 line segments? So how can we find that out? Well, this entire time, we've been using sides, the relationship between sides, to find the relationship between, well, this whole time we've been using the relationship between sides to find the relationship between areas. But this can go the other way as well. We can use what we know about areas to find the relationship between sides. And do you spot another pair of triangles that also use the same basis, BF and C? Take a minute. What other pair of triangles do you notice? Well, you will notice that another pair of triangles that also use the exact same basis is the triangle and right? They have the same height, but their two bases are different, and they're exactly the ratio between BF and FC. So what is the ratio of their areas? Well, their areas are respectively 2 to 180, which is equal to 1 3. Therefore, the answer to our question here, what is the ratio of BF and FC? Well, the answer to that is 1 to 3. Why? And this we have both things that we were looking for. We have the total area, which we know is 120, and we have the ratio of the sides, which is 1 to 3. Now all we have to do is solve. So we know the total area is 120. Multiply that by y over y plus 3y, which is equal to 120 times 140. This gives us 30. So the final answer to the problem is that triangle ABS has an area of 30. And remember, this is a very good example when it comes to geometry problems that you see in AMC 8. Things like this, especially with triangles, come up all the time. All you need to know, though, is when you're comparing triangles, you only have to look at their base and their height. And you can use the ratio of sides to predict areas, and at the same time, you can go the other way. Use the ratio of areas to sides. Thank you so much for watching.